Welcome again to the NPTEL course on storage systems. In the previous class, we took a look at fiber channel and we looked at some of the issues regarding fiber channel, especially bandwidth aspects, okay, how much throughput it can give, etc. In today's class, we will continue, but we will start looking at, instead of the fiber channel interconnect, we will start looking at Ethernet kind of interconnect, and then we will go into something called iSCSI, another protocol which is layered over Ethernet, SCSI protocol layered over Ethernet. Now, if you look at fiber channel, historically it has been very expensive because it is you might call it a niche market for storage only, and typically the port cost of fiber channel has been much higher than Ethernet, almost a factor of about, I think, about 10. So, invariably Ethernet has vanquished other protocols. So, all other protocols have usually become extinct, where Ethernet has been becoming stronger over a period of time because of the volumes and because of its simplicity of the basic protocol. So, generally people believe that from 1 gigabit Ethernet to 10 gigabit Ethernet is, when it happens, it will become very low cost. Therefore, everybody is thinking that if there is a way to lower the cost of storage, you might have to move to something like 10 gigabit Ethernet. Of course, 10 gigabit Ethernet is already quite strong in the core part of the network, the internet, but in a departmental setting, it is still not that common. So, if and when this happens, when the transition happens, then you might be able to easily encapsulate fiber channel frames in Ethernet packets. This is what is called FCOE. The advantage of this particular model is that since a lot of the enterprise storage is based on fiber channel, you basically, the software does not have to change. All you have to do is to change some of the switches and some of the adapters. Okay. So a lot of people believe that this might actually happen. So you can see a lot of increasing usage, but it's too early to say what is going to happen. Other option is, if you really want to exploit what is generally believed that 10 gigabit Ethernet will actually become very predominant, then you can probably drop the storage protocol specifically crafted for storage, the fiber channel protocol, and move to some other protocol which can be also used to transport SCSI. One option is to go to TCP IP. Okay. So, one idea is to use TCP IP as the transport protocol. So, the iSCSI actually stands for Internet SCSI. That means that my device can be anywhere on the internet and it should speak the SCSI protocol. So, if I have a SCSI device, I should be able to access it on the internet. So, the idea here is you take the SCSI commands, encapsulate within a TCP connection. Okay. What is the advantage? You can use existing network infrastructure. There is only one network for storage and data, and as I mentioned before, it can ride on the rapid growth of Ethernet infrastructure. Okay. Nowadays, you hear of something called Metro Ethernet. That means Ethernet that is available in a city. Okay. And so, if you have Metro Ethernet in a city, you can negotiate with providers for 300 megabit per second or 400 megabit per second, etc. Those kind of bandwidths you can negotiate, and all of this, of course, as I mentioned in the previous class, goes on fiber. Okay. So, the basic idea is that iSCSI could be lower cost per port compared to fiber channel. One advantage of going to internet is that it supports authentication protocols and specifically IPsec. Okay. Now, if you look about fiber channel, it was designed without security in mind, because general assumption was that fiber channel kind of devices will sit in a data center, and that's got physical security. Whereas, if you look at internet, it has always been, in the beginning it was designed for let us say regular use without thinking about security, but later the security aspect has been added onto it, and now you have something like IPsec. Even though there are problems with IPsec, it is still a good protocol. It is may not be the best, but it is a good enough protocol, and a lot of people are using it. Okay. So the thing is, if I go to iSCSI, one advantage I have is that I can just directly use the security mechanism that's available for IP. And the good thing about going to IP is that it's a widely used protocol. So whatever advantages you get because of the widespread adoption of IP, all of it naturally comes to you to for your SCSI also. Okay, that's one thing which is very strong with respect to going to iSCSI. The only difficulty could be that internet being a assemblage of widely different types of devices and interconnects, you may not be able to guarantee certain let's say delays, for example. You might have different types of delays, which is a big problem. If there is some way to handle this problem, iSCSI could be a real good contender. Okay, the basic issue is that internet is highly heterogeneous. So how do you ensure that you have reasonable guarantees with respect to delays? Diagrammatically, you can look at iSCSI as follows. You will have a physical interconnect between two links at the link layer. Of course, you have IP, and then you have a TCP connection, actually multiple TCP connections between at the TCP level. On top of it is iSCSI, which is basically the protocol which essentially encapsulates SCSI, okay, onto using TCP. And so essentially what we are talking about is SCSI's application. iSCSI is some kind of presentation layer, and TCP is the protocol. That's basically what's happening. Again, there are varieties of iSCSI possible. You can have a purely software iSCSI. That means that your host does all the processing with respect to both TCP IP processing as well as iSCSI. In a sense, this is completely done in software, whereas the adapter is a regular Ethernet card, NIC, what you might call vanilla adapter card you can directly use. Or you can attempt to move some parts of the functionality that is in software into hardware, precisely because this part of it can be, especially the TCP IP part of it, is very expensive to be done in software. So that is the basic idea about what is called TCP offload engines. The TCP offload engines basically take care of the TCP processing in hardware, and then the software only has to handle SCSI and iSCSI part. So these one other types of adapters. And of course, the final thing would be that the host only speaks SCSI protocol, and all the adapter which is connected to the CPU, okay, it speaks SCSI protocol directly, but using iSCSI as the medium, as the way to send commands and receive commands. So this also is possible. So there is a lot of possible configurations. This being lowest cost in terms of lowest and slow, this could be probably the more expensive one and probably much faster. So again, just to reiterate, iSCSI, what we do is we map the SCSI block oriented storage data over a TCP IP. Now notice that TCP IP is, it doesn't have any, it's what is called a stream protocol, and you have to essentially now layer on top of it something which has got a structured way of sending the data. Okay. So there is some small conflict between the TCP IP's model and what SCSI is doing. Okay. Of course, you will see this problem in a lot of places. If you look at SSL, there also you will see that it is what is called it's got some structures that has to be sent. So it is not really a string protocol that we are going to use. So here what we do is in iSCSI, we create a session between the SCSI initiator and the target, SCSI target. What's the session? It's a group of TCP connections linking an initiator with the target target, and this particular session is identified by a connection ID. Okay. So basically, it's a group of TCP connections linking an initiator with a target, and this group is identified by connection ID. Now, because SCSI requires ordered command delivery, iSCSI has been specifically designed with some sequence numbers so that you can support ordered command delivery within a session. Now, since iSCSI uses TCP IP, the throughput of iSCSI is going to be determined by what TCP can provide, and typically there is something called TCP Congestion Control Algorithm that we will discuss soon. That basically governs how much throughput you get in iSCSI. If you look at fiber channel, we had various classes, and the class that is widely used is the one which has got buffer to buffer flow control. It doesn't have, even though there is a class 1 which has got end-to-end flow control, the one which is used in fiber channel mostly is the class 3, which is got only buffer to buffer. Basically, because if you want to do end-to-end control in fiber channel, you require the switches and all the fabric of fiber channel to incorporate aspects like what TCP is doing, congestion control, whatever, okay, some mechanisms, so that there is a way to get as much throughput as possible through the fabric. And so there has to be some fairly complicated or substantial infrastructure that has to be there in fabric, so that you get the throughput that is possible in the fabric. Now, in fiber channel, as far as I know, this particular exercise has not been done seriously. So all we have is basically buffer to buffer flow control, and because of this, the kinds of throughput that you can get with TCP are still not possible with fiber channel. Okay, that's a basic issue. Basically, TCP has got end-to-end flow control from the beginning, whereas fiber channel, in spite of its design of class 1, it is generally now using only class 3, which is basically buffer to buffer flow control. And so it doesn't have an idea about the end-to-end aspect even today, okay, in spite of its class 1, okay, in practice. Therefore, iSCSI throughput can be better than possibly fiber channel, okay, especially on wide area networks. Okay. There are other parameters in iSCSI, for example, max burst length, that also determines how much of data can be sent out in one burst. Okay. There are other controls in the system. We just briefly look at the iSCSI, how it works. Again, you can see that it's basically encapsulating the SCSI commands in TCP. So you basically standardize how it is encapsulated with various fields, etc. Okay. For example, the SCSI write command is going to be, there is going to be a structure that is going to take each of the fields of the SCSI write command and then actually specify the standard, specifies how it has to be encoded. So you will write the SCSI write command, you send it from the initiator to target. Again, just as usual in SCSI, the target has to allocate the buffers and be ready for getting the information from the iSCSI initiator. So it has to send a ready to transfer. Okay. Again, this ready to transfer SCSI command has to be encapsulated into a particular TCP on TCP, so with a particular structure. Okay. And that is basically the RDMA. Again, the same issue with respect to when the initiator sends the data. This also has to be encapsulated in a protocol data unit. This is basically iSCSI data out PDU, and then the response also comes back. Okay. As I mentioned earlier, you also need to do other control management aspects. For example, you have to establish an iSCSI session, which essentially means you have to create one or more TCP sessions. Okay. And you might also, if you are using IPsec, you might also have to use a security negotiation. Again, IPsec has a particular phase in which you negotiate what kind of protocols are using for security. For example, Diffie-Hellman or whatever. Okay. There are various methods. There are actually 6 methods for types of security, let us say, mechanisms present, and also some of the parameter negotiation. Like I mentioned before, you may want to negotiate what is the max burst length. Okay. So all those things happen as part of iSCSI. Okay. So now let's look. We had a look at Fiber channel, how it does flow control. Basically, it's credit based. We will look at iSCSI flow control. First of all, as I mentioned earlier, iSCSI is laid on top of TCP, therefore depends on TCP. Now, TCP uses sliding window for flow control, but also uses what is called congestion avoidance algorithm. The issue with TCP is that TCP assumes that the end devices are intelligent, but the network is dumb. Because the network is dumb, it is understood that it does not have any mechanisms to help you realize the throughput that is possible. That means it has to use some way of probing the system to figure out how much bandwidth is there, and therefore it has to use some slightly sophisticated control theoretic model, and that control theoretic model we will discuss soon, and it is typically called as a congestion avoidance algorithm. Now, on high speed networks, the typical TCP that we use, TCP Reno. For example, Linux supports TCP Reno and also something called Cubic right now. It had supported other models also before, but right now the most common one is TCP Reno. It turns out that TCP Reno underutilizes network bandwidth. I will again explain what this means. I'll show exactly I'll give further details. So, because if you are using iSCSI and you want to get as much bandwidth as possible, because typically storage requires high bandwidth. If you are doing backup, any of those kind of things, it's going to require huge amounts of bandwidth. So the idea it's especially important for us to use the network bandwidth well. Okay. So since TCP underutilizes network bandwidth, we need to have different models of TCP. So there are various other types of models that have been proposed. We will look at few of them in some briefly. For example, there is something called scalable TCP, HTCP, BIC, cubic TCP, etc. As I mentioned, cubic TCP is the one that is currently there in Linux kernel, recent versions. Sometime back, there used to be something called BIC, which is no longer available in the standard Linux kernels available. Now, another issue about iSCSI is that you can, as I mentioned, you can have one or more TCP connections. With one or more TCP connections, it's possible to increase throughput, but there are some problems. Okay. If you have concurrent connections, they can compete for bandwidth, resulting in unfair sharing. And TCP by definition does not have any such models of how to make sure there is fairness in it. And also there are some problematic aspects of TCP. There are what are called synchronization aspects. For example, if there is a loss, if a packet has been sent between two nodes and there is a loss, then the kernel implementation of the TCP is common to all the flows. So because of a loss on one, it will decrease the amount of stuff each flow actually is going to send out. Because each flow is now decreasing it, then the cumulative amount of stuff that is being sent also decreases across all the flows. So suddenly you can see a dramatic drop in all the flows. So in a sense, it gets synchronized. All the losses get synchronized across all the flows, and therefore it can be somewhat problematic. Basically, the congestion information needs to be shared among all the concurrent connections. I need to come up with some newer models, like some people have called it fair TCP. Okay. Again, I'll go into some of the details in some detail. I'm just giving you the high level ideas, what exactly are the kinds of problems when you take something like TCP, which was not designed for storage purposes, used in a storage context. Okay, this gives you a diagrammatic way of understanding what could be going on. it turns out, as I mentioned earlier, the end devices are intelligent, the network is considered to be not so intelligent. That means that if you do not have any, let us say, take care of what the kind of situation that could develop, you might get into what is called uncontrollable congestion. For example, the red line, like this. Why is this happening? The reason why this is happening is because TCP, nobody tells TCP how much bandwidth is there, because I can suddenly connect my laptop here and expect to talk to some other party somewhere else, right? And no information is given to the laptop saying this amount of bandwidth is available. That means this particular laptop has to probe the network, find out how much bandwidth is there, and it has to do it in real time. Okay. Now, this is somewhat different from if you are talking about fiber channel, etc. In fiber channel, it is a more structured environment, and you essentially tell each of those fiber channel entities some number, you give it some number of credits. And so, in a sense, it is a slightly more structured environment. Here, it is basically totally unstructured. So, what does the TCP IP do? It starts pumping packets to see how many packets can be sent before some kind of loss occurs to the flow. So, if suppose 100% is the maximum capacity in the system for that particular connection between my laptop and something else, I will keep on increasing my number of packets I send up to this point, and then suddenly I experience a loss. Now, if once I experience loss, then I have to back off. I can't be sending at the same rate, because I notice that I cannot be doing it. There are various models. The first simple TCP model was to come back to ground 0 and start again. Again go down to 0 and come back again. Now, basically we can see that with this kind of model, you can essentially get, if you integrate the area under this red curve, that is essentially the amount of bandwidth you have. Okay, you average it. Essentially, we are getting some closer to possibly half or close to that amount of bandwidth available. Okay. Now, if you do some congestion avoidance, probably you are going to be in this blue category. Okay. You increase slightly more gradually, you do not overshoot as much as this guy possibly did, but you do it slightly gently, and then you suffer some losses, you slightly contain it, you do not go all the way to almost ground 0, you go slightly lower and somehow try to figure out a way of doing it slightly better. This is an example of managed congestion for internet. Ideally, what I want for storage is something like this. I want to discover the let us say the capacity and hopefully stay constant like this. If I can do it, then it's the best for me. Okay. This is what I would prefer, because this is what we normally do in a data center kind of situation. We can essentially get this kind of throughputs, consistent performance, and because for storage, backup is an important aspect. So, for those kind of things, it's really important to be able to say how long it's going to take, because they take a long time in the first place. So, I need to have some kind of a idea about how long it takes. Okay. So, ideally, I would like to be in this category, even though it's not 100%, but I want to be consistent performance is what I'm looking for. Okay. So, the idea is how does iSCSI or any other model that rides on top of TCP, how can we make this happen? Okay. That means we have to understand the TCP models. Okay. Again, just to summarize some of the things what we talked about, TCP is basically a peer-to-peer protocol. It has got intelligent end devices and dumb network. You have to estimate bandwidth available, and unlike fiber channel or a telephone network, there is no setup before transmission. Therefore, it has a control theoretic model, and basically the acknowledgements that you get essentially clock the protocol. That essentially tells you how to go forward. So, the standard method is in TCP is to you start from ground 0, you increase exponentially. That is what you do is you send one packet, see if it comes back. If it comes back, then you increase the, you know that there is capacity for 2 packets, because one came back and you sent one and came back in one round trip. So, there are 2 packets already were in flight. So, now we can increase it to, you send 2 packets and see if both the 2 packets come back, the X come back for it. So, it becomes 4. Then you again increase it by factor of 2. So, you keep on increasing it, that is basically exponential increase till you hit a threshold. After a threshold, and this is determined by some other parts of the system. You basically increase it additively, because if you just go exponentially, you are going to definitely hit a loss very quickly, and it can essentially, what it can do is the network can get overloaded too fast. So, the idea therefore is not to go all the way till the packet loss happens. The idea is to increase it in a more gradual manner till you actually hit the loss. So, without overloading the network. Now, once you hit the loss, the idea is to cut back, you sort of back off from the network, and that is where what is called multiplicative decrease happens. Okay. One important thing about TCP is that the losses indicate lack of capacity network. It is a very critical function. It is not some optional thing. Without losses, you can't figure out how much bandwidth is there. So, it is part of the network protocol. Okay. It is not something that can be dispensed with. Whereas, if you look at fiber channel, etc., losses are a serious problem. It is not expected that you lose things. Okay. So, because there is no serious attempt at probing the network in the case of fiber channel, it is mostly set up. It is set up beforehand. Okay. Whereas, here you have to probe the network, you have to suffer losses, then you figure out what is going on. Okay. So, there is a big difference in the way perspective in the first place. Okay. So, for each connection, TCP also maintains a congestion window which limits the total number of unacknowledged packets that may be in transit end to end. Okay. So, this is what is called the congestion window. Okay. So, if you want to really do good in TCP, you have to keep if you are doing on a wide area network, you have to be sending packets so that the various routers, etc., they buffer your packets. So, essentially that pipeline between the various routers, they are kept full. One way to do it is have multiple concurrent sessions and sending large data units. That means you need to have large TCP window size. Okay. Again, because it is the flow control, that window size essentially tells you how much you can send out. So, the TCP throughput is proportional to MSS by RTT into square root of P, where P's are the random packet loss probability and MSS is the maximum segment size. Okay. So, the way to increase throughput is to increase MSS or decrease your probability of losing packets, or make sure RTT is small. Okay. This is the only way to increase throughput. Okay. Now, in the case of fiber channel, the throughput is given by number of credits. Of course, in fiber channel, you can increase credits, but somebody has to do end-to-end control, which is not currently there in most fiber channel usage right now. Okay. So, of course, fiber channel also has RTT as an issue. So, that also is inversely proportional to RTT. Okay. The one major difference between fiber channel and TCP is that your TCP performance depends on the loss, whereas fiber channel, as far as possible, does not want to see any loss. It is basically a storage protocol, because it is designed for a different reason. Okay. So, again, how do you achieve high TCP performance? Large window sizes. You can also use what is called jumbo frames. So, the TCP segment size can be matched closer to the Ethernet jumbo size frame size, which is about 9000 bytes. Okay. Typical Ethernet is 1500 bytes, whereas jumbo frames are 9000 bytes. You can use also what is called selective acknowledgements. Normally, TCP uses something called cumulative acknowledgement. Here, in selective acknowledgements, you can send a bitmap which tells you which of them actually succeeded in going, which of them didn't succeed. You don't have to retransmit those portions that could be done with the cumulative acknowledgements. Okay. So, this is useful when the medium is dropping many packets, and this is sensible because if iSCSI is going to do it across the WAN, this may be appropriate. Again, as I mentioned before, you need to do traffic shaping or rate limiting. We already discussed this part, and the most important thing is you have to avoid packet drops if possible. Okay. Why is that the case? Because it turns out if you are going to have packet drops, then the TCP retransmit mechanism actually takes a long time. Okay, I will come to this soon. Basically, because you are going to be in the additive phase in the TCP protocol, so the ramp up is going to be quite slow, and because it is going to be slow, you are going to have serious problems with respect to achieving the full bandwidth. Okay. So, to let us just quickly look at some aspects of how this TCP performs. Okay. So, this is the what is called the rapid increase, the exponential phase. Then you suffer a loss, it comes down. Then you have a linear increase. Again, you suffer a loss, you come down. So, basically, this is the threshold what I was talking about. So, there are multiple types of TCP. So, in the beginning, this one basically ramps up all the way to the beginning, to the maximum to the capacity till it hits the loss. Then it cuts down to half the capacity and again slowly ramps up. So, this is going to be a sawtooth pattern like this. Okay. Now, this is a round trip. Basically, you can see start from here. Sorry, I made a mistake. Okay. So, basically, the throughput of this is determined by 3 parameters. One is called the congestion window, that is the number of packets that are out in the flight. The receiver window, how much the recipient party can accept. The sender window, basically how much it has buffered from the application. Okay. Normally, we can assume that receiver and sender windows are fairly large. So, the only thing that limits your performance is congestion window. Okay. Now, as we saw just now, this change in the congestion window, it's like this, right? Essentially means that you are not able to hit the capacity. Okay. So, you are essentially not going to see the full capacity. Okay. Now, people have used this kind of this sawtooth kind of patterns, and if you integrate over this area, you will essentially get the amount of bandwidth that is available in the system, and that is how you get that 1 by root p and 1 by RTT factors in the bandwidth I showed you before. Okay. So, let us just look briefly at the various models that TCP has got. Okay. TCP Reno, basically what it does is, if it uses, as I mentioned, it uses additive increase. For example, here this is the additive increase part and this is the multiplicative decrease. Okay. So, you are going slowly one by one like this, and then once the loss is there, it drop dramatically. Okay. So, this is basically new congestion window is basically old congestion window plus alpha times old congestion. Basically, what it means is that this is the proportional increase. So, if you multiply by old congestion window, it's basically you are increasing it by alpha, the packet, the new number of new packets that you can, additional packets you can say is given by alpha. Okay. The loss is going to be given by as a proportion of the old congestion window by factor of beta. So, that in Reno basically what happens is that if you are in the additive phase, if you get an ACK back, you can send one more extra packet. Okay. That is suppose you are sending 100 packets, you can send next time around 101 packets. Okay. So, our basic problem is that this ramp up phase can be very, very slow, because you can see, right, you are sending one extra packet every round trip. Okay. So, it will take C by 2 round trips before I can go from here to here. Okay. Now, if I am able to send out 1000 packets, let us say my capacity is 1000 packets, that means I have to wait 500 round trips before I can get back to this, okay, which is very slow. Okay. For example, you have 1 gigabit per second link. Okay. Nowadays, these are available in wide area networks. 1 gigabit per second is definitely possible. Yeah, 1500 bytes packet size, 100 millisecond RTT. Then Reno will take full 14 minutes to achieve full utilization following loss event. That means that in the previous example, suppose I am here, I suffer a loss event, I come down here, it will take me 14 minutes to get to this. It is excruciatingly slow. Okay. So, this additive increase is a bit too, it's a bit too slow. Okay. So, people wanted to see if it is possible to do something better. Okay. So, there is scalable TCP basically does that. Instead of, in the previous one you had we had increased proportionality with respect to congestion window. Here we directly increase it by alpha, okay, and it is 0.01. Okay, loss is exactly the same as before. Okay, this is slightly faster way of ramping up in the additive phase. The other models also, I am not going to go too much into it. There are things like, for example, you can both play around with the alpha and beta, you make it adaptive. So, for example, I will just briefly indicate what this does, TCP does. There is, as I mentioned, it is adaptive. So, there are two modes, low speed mode and high speed mode. So, the alpha is some value in the low speed mode. In high speed mode, it is slightly bigger, and it is decided upon depending on the time elapsed since the last congestion event, and this alpha h delta is basically some function of delta and delta L. Okay. Some people have tried using this also. Now, there was another thing that was attempted, BIC, and this was actually present in Linux kernel for quite some time, 2.6.8 to 2.6.18. This is called the binary increase congestion. Basically, as you can see, the idea here is to see if there is a way, instead of going gradually from here to here, to see if you can go from here, go to some in between position, etc. Okay, see if you can do binary search. Okay, the idea, simple idea is to do binary search. Why go linearly one by one? Do some kind of binary search. Okay, you suddenly jump here, see if it is okay. If it's not okay, keep increasing it by some suitable factor. Okay. So, it consists of two parts, binary search increase and additive increase. So, given the minimum and maximum window sizes, set the target window to midway between the two. Just like in binary search, you want to look at in between first, same thing. Okay, you target window to midway between the two. You find that there are no losses at this point, then current window becomes the new minimum and the new target becomes calculated. Okay. So, what is the lower value becomes the current window becomes the lower, the minimum, and again a new target in between value is calculated again. If there is a loss, then the current window becomes the max, and then you reduce the window size, and that becomes the minimum. Okay. Essentially, what is happening is that you are aggressive initially, but it gets less aggressive as the window size approaches the target. Okay. Now, it turns out that this also can get into some problems, basically because if the difference between current window and target width is very large, then directly increasing it might stress the network. So, to avoid this kind of stressing, you can define some thresholds. So, basically you come up with the difference. If it is bigger than that threshold, you actually increase it only by the threshold, till finally you come to the difference is less than the threshold. Okay. So, various people have tinkered with this kind of algorithms, and various improvements have been made. Currently, actually Linux kernel uses a modification of BIC, it is called TCP cubic, where the window size is a cubic function of last time since last loss event. Okay. So, this has been experimentally shown that it works well in wide networks with large bandwidth delay product, and essentially it is a less aggressive and more systematic derivative of BIC. I think the details one should look at the papers. So, this has been there in Linux kernel and is currently there. Okay. Standardly, it comes in Linux kernel. Now, given that we have talked a bit about TCP, the question is, for iSCSI, what do we do? Okay. Now, there are various possibilities. I mentioned last time that one important thing about storage protocol is that it should be zero copy. If it is not zero copy, then you are going to suffer great difficulties, especially from the CPU utilization point of view. Okay. Now, for that reason, there has been some standards called RDMA over TCP, okay, and which essentially guarantees zero copy, and it has been standardized as a particular protocol, Internet Wide Area RDMA protocol. Okay. Now, as I mentioned before, TCP offload engines also attempt to do the same thing, but unfortunately TCP offload engines were done by various vendors in a proprietary manner. So, even if they have zero copy architecture, their ability to interoperate has been somewhat poor. Therefore, these standards like IWARP are better for achieving zero copy across various types of devices. Okay. So basically what we have right now is, I want to have zero copy. So one I can do is I can use RDMA over TCP, but I am doing iSCSI over TCP. That means that I can't directly use this RDMA over TCP. That means I need to find a way of extending iSCSI protocol that was layered over TCP. So it is actually layered over RDMA, because for me what the problem is that my original definition iSCSI was over TCP. Okay. But if I want to use zero copy, I need to have RDMA on top of TCP itself. So I need to essentially change iSCSI so that it is layered over top of RDMA, which in turn uses TCP. That also has been defined. This is called iSCSI extension for RDMA, ISER, and basically this combination of iSCSI, RDMA and TCP, it eliminates TCP processing overhead from RDMA capable NICs. Okay. There has been another effort called SCSI over RDMA, or SRP, which I am not very sure, but I think it is not that very popular. Okay. So that also has been attempted. Okay. So it is basically directly, instead of going through iSCSI, this is the original protocol that came in the early 2000, it directly tries to layer SCSI over RDMA. So what we are talking right now is iSCSI over RDMA over TCP. Okay. This seems to be the one which is used, okay, currently. Okay. Now there is another interconnect called Infiniband. Okay. Now initially in the early 2000, this was proposed as a system to system interconnect. So the basic idea is that when CPUs have to talk to each other, you have a multi processor system and you need high speed interconnect. Then Infiniband was proposed as a system to system interconnect, and this also it has become widely available, and it is widely used in high performance computing for high speed, because of its high speed. For example, it is very easy to get 40 GB per second kind of connections. It is not that difficult. So, and actually if you look at the Infiniband roadmap, people talk about 120 gigabit per second, 200 gigabit and 300 gigabit per second. So, high speed is certainly possible. And so, if you look at all the top 500 machines worldwide, you will find that a good number, probably more than, I don't know, close to half or so, I am not sure exactly the amount, they use Infiniband as a system to system interconnect. So, because of the wide availability of this interconnect, the idea would be, why not use it for storage also? Okay. That is basically the original plan. Somehow it didn't take off that easily in the beginning, but now I think because of the widespread use of Infiniband in high speed systems, I think it is going to likely to come back again. One thing about Infiniband is that it has some quality of service models as part of its specification. It also handles some failover aspects, and so it's a slightly more complex specification compared to Ethernet. Okay. And it's not clear how much of all the specification, for example, failover or quality of service is widely available in all the products, but the specification is has got quite a few substantial support for quality of service of failover. Okay. So if such a thing is available, the natural thing would be to use it for storage interconnect, and then again here also we need to make sure that somehow you do not have extra copies, because extra copy is going to kill your performance. So there is a RDMA over Infiniband also available. Okay. So this also has been defined, and I think many at this speeds like 40 gigabit per second, etc., without RDMA you cannot really survive. Okay. So for CPU to CPU in large scale transfers, RDMA over Infiniband is necessary, and I think as far as I know it is widely used. Okay. Now, one peculiar thing about Infiniband is that compared to SCSI or other TCP IP, etc., many things have been left slightly underspecified. Okay. So, for example, it has a notion of what is called verbs. Okay. That means these are certain types of functionality that has to exist. For example, I should be able to send something, I should be able to receive something, but most of the parameters are not really spelled out. The reason why this is the case is because it has to interact if it is basically based on something called the via specification, and that tries to ensure that as little extra copies are made as possible, and therefore it turns out that some of the things interact heavily with other aspects of the system, especially operating systems or kernels, and so they have left it sort of open. Okay. And so it's a slightly it is very well specified with respect to some areas, like for example quality of service or failover, etc. But in terms of the API itself, it seems to be underspecified, and so this is one issue with respect to Infiniband. But there are attempts at there are various types of let us say standards that have come up in addition to the main standard, so that there is possibility of interoperability. Okay. So given that it is highly used in HPC area, so that means that in spite of this underspecification, it's still not a problem. Okay. So let me summarize what we have done so far. First of all, we looked at in the previous class, we looked at iSCSI, we looked at SCSI, and then we saw how fiber channel can be used as a way to transport SCSI protocol. Now, fiber channel is very well suited for as a storage protocol, but storage is somewhat of a niche market. Because of that, the cost of fiber channel has been typically very high, and so the trend towards is being to figure out how to reduce the cost of this fiber channel kind of based models, interconnects. So the idea would be to see if there is some way to move towards a slightly different kind of model, and the model that is most attractive is somehow go to gigabit Ethernet or 10 gigabit Ethernet. And so iSCSI is one model. There is a evolutionary path, what I mentioned as FCOE, fiber channel over Ethernet, which is an evolutionary path. Now, it turns out that this is becoming available also, except that it also has certain complications. Okay, I have not really gone into it, but it turns out that if you want to use FCOE, then there are certain subtle aspects of the protocol in fiber channel. For example, when a particular switch fails in fiber channel, there is some way to recover from it. Okay. Now, that specific way in which you recover from it also has to be made appropriately available even if you use Ethernet. That means that you are the same kind of semantics that was there in a pure fiber channel network also has to be made available on Ethernet network. That means that there has to be some more extra infrastructure that takes care of those issues. So, even though it is an evolutionary path, it also entails certain additional complexities, and but I think it's being attempted, it's being done. Of course, you are losing something also when you go through this particular path, basically because you are not able to guarantee certain latencies, because the Ethernet protocol has a different model. Okay. So, iSCSI is becoming popular, but as far as I can see, 10 gigabit Ethernet has not yet become widespread. Therefore, its use has not become that dramatic within a departmental setting. Okay, it's still not happened. I think probably in about next 5 years or so, if 10 gigabit Ethernet becomes very common, then iSCSI could be used as a protocol, but it's still not the norm right now. Okay. Now, for all these things, it turns out RDMA standards are very critical. Without RDMA standards, there is no possibility of zero copy, and so this basically there has to be a lot of standardization around RDMA, and a lot of effort is going here, and it is taking a lot of time to stabilize this particular issue. Okay. And if you look at Infiniband, they are very strong in the HPC environments, and because of this attractiveness about the kind of installed base of high speed 40 gigabit per second or 20 gigabit per second kind of ports, one can, many have been attempting to use it for storage, and I think it is also picking up. Okay. So currently it's a bit of confusing situation. There is no one strong interconnect that is available. The only thing that you can say is that iSCSI on the top is everywhere and fiber at the bottom is everywhere. In between there is a lot of churning going on, so we will not know exactly what is going to happen, but it is very likely that gigabit Ethernet actually will finally take over, but it's going to take some time. With this I am going to conclude this particular lecture.